In this lesson, we will quickly discuss the off-grid and grid-connected PV systems, and we would try to evaluate some calculations, and after that we will go to another topic entirely. Now, on my left, this particular building has a PV system installed on it, and the one on the right here also has a PV system installed on it. You might want to look at both buildings and ask which one has a grid-connected PV system and which one has an off-grid PV system. Evidently, you will notice that this particular building has a grid-connected PV system because of this structure you'll see here. This structure represents a connection to the grid, the utility grid. And then you can see the PV modules arranged on the roof of the house, and then you can see all the other necessary connections needed, and then from the connection from the distribution panel you can see how this is connected to the grid. And then this other building, you will notice that there is no utility grid connected to it, so this is an off-grid PV system. It is a standalone PV system that is not connected to the grid. So let's quickly look at some of the features of these PV systems. The off-grid PV system is isolated. It is not connected to the grid. It is more expensive because it has to have a battery incorporated into it, and incorporating batteries into PV system would mean that we are trying to add storage to it, and when we add storage to PV systems, it increases the cost of such PV systems. Again, it has a longer payback period compared to the grid-connected PV systems. It needs battery to store power, and batteries need maintenance. So that means the cost of maintenance would also increase compared to the grid-connected system. Now, for the grid-connected system, it is fed by the grid and by the PV system. This house that has a grid-connected PV system is fed by the grid and at the same time fed by the grid-connected PV system. This simply means that when the PV is not working, we collect our energy from the grid, and then when the PV system is working, we collect our energy from the PV system. At times, the times when the PV system do not work would include in the night when the sun is not shining, or in the winter times when we do not have enough solar radiation to power the PV systems, and we definitely have to continuously use our load in the house. So at such occasions and some other occasions that may occur, it is possible that we may not be able to get enough energy supply from the PV system. In cases like that, this kind of a building, this kind of a house will collect their energy from the grid. So there will never be a time where they will not have energy to use in this particular building, all things being equal. And when the grid is not available and there is enough solar radiation, this kind of a building would continue to collect their energy from the PV power system. Again, it is less expensive compared to the off-grid system. You can see the comparison in price, it's like 1/3. The cost of installation of the grid-connected PV system is about 1/3 of the cost of installation of the off-grid or standalone PV system. Again, you can see that it has a shorter payback period. That's another feature. It has a shorter payback period compared to the off-grid system. As you can see, the payback period for the grid-connected system is about half or less than half of the off-grid or standalone PV system. And the grid-connected system does not use battery. So this gives it a lot of advantages, and then you can see that the off-grid has its own features and advantages too. Whatever the case is, it is important to understand the difference between the off-grid and the on-grid or grid-connected PV system and be able to state the difference between them, the features of both of them, the advantages and disadvantages of both of them, and all the other technical details that needs to be known should be known regarding the two types of PV systems that we have. Now we'll look at some of the considerations that need our attention, that we have to pay attention to when when we are trying to design a PV power system. The first one is the electrical load consideration. What are the considerations that we have to pay attention to when we are talking about installing or designing a PV power system? The first one is the electrical loads. So the first question you want to ask yourself is this: according to the type of loads that the PV system is expected to meet or power, which is more important? Is it the total daily energy output, or the average power, or the peak power? So we have to think about these. Okay, the peak power represents the maximum power that can be supplied by the PV. The average power would mean over a period of time, what is the average power that this PV can supply over this period of time. And then total energy output would mean that, okay, how much energy is this PV able to generate in 24 hours, in 1 hour, in 2 hours, and so on and so forth. Okay, so are we going to pay attention to the energy or the power? If you are paying attention to the power, is it going to be average power or the peak power? These are some of the considerations we have to pay attention to when designing a PV system, and all of these are connected to the load that the PV system is going to power or meet. At what voltage will the power be delivered, and is it AC or DC? These are another set of questions that we must ask ourselves regarding the electrical load considerations of PV systems. Okay, what will be the voltage at which the power will be delivered? And then the energy that is being delivered or power being delivered, is it going to be AC power or AC energy? Is it DC power or DC energy? All of these questions must be asked. This simply means that we will have to understand the profile of the load to be met, or the need that is required to be met by the user. We need to understand the load appliances, the load applications. We need to analyze the load applications, and then from there we'll know exactly what is needed, and then it will be easier and more reasonable to know exactly what to supply based on what is needed, so that we don't oversupply energy or undersupply energy. In the case of oversupplied energy, we'll be spending too much money to meet very little demand. And in the case of undersupplying energy, we will not be able to satisfy the user and meet all the load requirements that are required to be met. Okay, the next question you want to ask when considering the electrical loads of PV systems during the design or installation is there going to be a need for a backup energy source? Is backup energy source needed? That simply means when the PV is not working, do we need a backup energy source? Either like a wind source or a generator or a grid or other kinds of sources, so that when the PV is not working, there is something else that would supply power. This is to ensure that at any point in time, there is no lack of supply of energy to the load requirement or to the load that should be met. Usually, the first things the designer has to estimate are the load and the load profile that the PV system will meet. Generally, the peak power is estimated by the value of the highest power occurring at any particular time. Here is a simple example to analyze how to design and how to profile the load or appliances that a PV system will need to meet. And we'll go ahead and look at how to design a PV system that can actually supply and meet the load that we have profiled for the user or consumer. The question says, estimate the daily and the peak power required by a PV system that has 3 appliances connected to it with the following characteristics. The first appliance, appliance 1, has 20 watts and is operated for 3 hours between 10 a.m. and 1 p.m. The second appliance has 10 watts and it is operated for 8 hours from 9 a.m. to 5 p.m. Then the third appliance is rated 30 watts and is operated for 2 hours from 2 p.m. to 4 p.m. So you can see we have the power ratings of the appliances, we have the duration of use of the appliances, and then we also have the specific time that the appliances are used. Now, what we are looking for is the estimation of the daily load and the peak power required by a PV system that has the following appliances, or that has 3 appliances connected to it with all of these characteristics that we have discussed. The daily energy use is going to be calculated as follows. We know that energy is equal to power times time because energy is measured in kilowatt hours. Power is kilowatt, time is hours. So energy is equal to power times time. And in the scenario given to us to analyze, you will find out that we have a power for each appliance, and then we have the time of use, the duration of use of each appliance. Total energy consumed by the first appliance will be 20 times 3, and that will give us 20 times 3. For the second appliance, it will be 10 multiplied by 8, plus the third appliance, which will be 30 watt multiplied by 2, and that will give us 200 watt hours. So total energy consumed by these 3 appliances will be 200 watt hours. To find the peak power, a time schedule diagram is required, and that is why when you look at this diagram, it will give you an idea of what a time schedule should look like. Let us check this diagram together. You notice that on the vertical axis we have the power rating. We have a graph of power against time. On the vertical axis we have the power measured in watts, and then we have the time measured in hours. So you can see from 0 to 24 hours on the horizontal axis. And then we will now try to profile our load. The first load, which is appliance 1, has a rating of 20 watts. And then it is used for 3 hours from 10 a.m. to 1 p.m. So when you look at the timings that we have here, the earliest time we have is 9 in the morning. So you come here and you look for 9. This is 9, and that applies to load 2, load appliance 2. So from 9 a.m. to 5 p.m. in the evening, that simply means that is when we have load appliance 2. So this 9 a.m. goes up this way, and then it keeps going until it gets to 5 p.m. That is 1700 hours in the evening. Okay, and the rating for that appliance is 10. So you will notice that this is traced to 10 watts. So this is the first load, which is load appliance 2. Then the next timing we have is the 10 a.m. load. Okay, after 9 a.m. we have 10 a.m. and that is appliance 1, and that is for 20 watt. Okay, so we will look for where 20 watt is. This is 20 watt here. Okay, so that means we'll just trace this up a little bit right from here to this particular point, and that load stops at 1 p.m. So on the horizontal, we'll trace it until we get to the 1 p.m. time, and then this is traced horizontally up until 1300 hours. That represents the 1 p.m. time. So as you can see, with the dotted lines, we have traced the load appliance 1 of 20 watt and 3 hours usage. That's exactly what we do have here. Then the third load, which has 30 watts rating and operated for 2 hours between 2 p.m. and 4 p.m. Will be given here. So what you would find is, for load 3, we have it's starting from 2 p.m. So this is 2 p.m. 1400 hours is 2 p.m. and then the rating is 30 watt. Okay, if the rating is 30 watt, what you would notice is that if you trace it from the origin, from 0 watt right up, dotted line, it will get to this particular point. So this is going to be the 30 watt load, and then you trace it down to 4 p.m. or 1600 hours. Okay, so this is expected to be, the dotted line here is expected to be the 30 watt load. Now I need to call your attention to something extremely important. You will notice that the load line has to be drawn. So for the load line, we'll continue the next appliance, which is 20 watt load. If you add 20 to 10, it gives us 30. So for the 20 watt load, you draw the 20 from 10. It's going to pick its Q from the 10. Okay, and then it goes this way. And then you notice again that for the third appliance or the third load is 30 watt. Then you add that 30 again to this 10, which acts as the smallest load. So if you add 30 to this, it gives us 40. So that it traces this right up here, and then you have 40, and then you come down and then you have your total load line. It is important to be able to identify the difference between the load line and then the load appliance. Load 2, this is a load appliance, and then when you are drawing your load line, it will be this 20 plus these 10, because this 10 watt is being used up by the load, okay, and then the other load is 20. It's going to start from 0 to 20, but since there is a 10 that has been used up here, the load line will be this 10 plus this 20 that is not coming in, and that gives us 30. That is why we are right up here. The same thing happens to the 30 plus 10, that gives us 40, and that's why we are right up here. Okay, so it is important to know how to draw this load line so that you, and to be able to tell the difference between the appliance's load and then the total load line for the curve that we are drawing. So we have a question here, and that takes our analysis further. A remote cottage has the loads listed in the table below. Find the average load and the peak power to be satisfied by a 12-volt PV system with an inverter. So you can see we have the appliance type, different types of load that we need to power with the PV. Then we have a description of each of the load appliances. Then we have the type of power that each of the load requires, and then we have the period of operation, the time of use of the loads. So the first load is lights, and then you can see we have 3 of those, 3 lights, each of them having a rating of 25 watts, and it's a compact fluorescent bulb, and it is used on a daily basis. It requires a DC power. So that simply means that before we convert the power from DC to AC using the inverter, we have to supply this first load, and it is used in the night for 5 hours. Then we have the second light, which is 11 watt compact fluorescent bulb. It is also used daily, but requires an AC power, and it is also used in the night for 5 hours. Again, we do have a water pump, and it is used on a daily basis too, requires a DC supply power. It is used during the day for just 2 hours. We have an oven, which is 500 watts power rating, and it is used just 3 times in a week. So this is used weekly and just 3 times in a week. And then it requires an AC supply of power, and it is used for just 1.5 hours during the day. And then we also have a steam iron, which is rated at 800 watt, used just once in a week, requires an AC power, and is used for 1.5 hours during the day. So this gives you an idea of the entire load that should be powered, the profile of the load, the description of the load, and then from here you know exactly how you can find out what the energy consumption of these appliances would be. So the first thing we want to do is to quickly make a little rearrangement. You can see we have the appliance type, we have brought the power to the side, and then we have decided to calculate the total power for each appliance. So this column is known already, this column is already known, we just moved it here. Then this third column, we just created it, and we created it from the description given to us. So we were told that we have the first light, we have 3 of those, each one of them is 25 watts. So 25 multiplied by 3 will give us total power drawn by this first light, by the DC light, and that is 75 watt. Okay, and again, as you can see, we were told that the run time is 5 hours, and then to find the energy for that, it will just be power multiplied by the duration of use, or the run time, and that gives us 75 times 5, which is equal to 375 watt hours. This is per day. This is energy per day, 375 watt hours per day. So if you want to convert these to weekly, this gives us 2625. 375 multiplied by 7 will give us what we need. Total energy per day is 375, and then if you multiply the daily energy by 7 days that we have in a week, it will give us total energy we need per week. So 375 multiplied by 7 is what gives us 2625 watt hours, 2625 watt hours. You can see we have daily profile, we have daily energy profile, and then we have weekly energy profile. This is because we have some of our appliances used daily, some of them are used weekly. So it's important we have both of them here handy so that anytime we need to use any one of them, it will be easier to assess. All right. Then the second light is AC. It is 11 watts. It is run for 5 hours. That means total energy per day will be 11 multiplied by 5, and that gives us 55 watt hours. In a week, that will be 55 times 7, and that gives us 385 watt hours. Then for the water pump, which is a DC type of power that will be drawn, we have 50 watts, and then the runtime is 2 hours. Energy per day will be 50 times 2. That gives us 100 because it is used on a daily basis. That gives us 100 watt hours. On a weekly basis, that will give us 100 multiplied by 7. 100 multiplied by 7, and that gives us 700 watt hours per week. Then the oven, which is used per week, we were not given the daily use of oven and steam iron. That is why you notice that I do not have daily profile here. However, if you choose to find out an average daily energy profile for oven and steam iron, you can do that by just dividing the weekly energy by 7. That will give you an idea of the average daily use. But from the question, we've been told categorically that this is not used daily. This is used weekly and probably twice in a week or once in a week or 3 times in a week. So we just need to factor that into our analysis. Okay, for oven, which is AC, we were told that it is 500 watt. It is used for 1.5 hours. So 500 multiplied by 1.5 hours multiplied by 3. Since we have been told that it is used 3 times in a week, and that will give us 2,250. That is why we have that here per week. If you want to know the daily use, you just divide that by 7, and that will give you the average daily use of the oven. If we have to calculate that, that will give us about 320 watt hours or thereabout. Okay, then we have the steam iron that is used just once a week. So we have 800 multiplied by 1 multiplied by 1.5, and that will give us 1,200. So you can see that we know total energy consumption by all the load appliances on a daily basis and on a weekly basis. So now let's begin by calculating the average DC load. In the question, we were actually asked to find, we were told to find the average load and peak power to be satisfied by the 12-volt PV system. So let's quickly do that. What is going to be the average DC load? You will notice that for the DC, this is what we do have. How many DC appliances do we have? Just 2 DC appliances. The lights, which is the first light, and the water pump. So total energy by the water pump is 100. Total energy by the light per day is 375. The DC lights per day is 375. So you can see we have average DC load will be equal to 375 plus 100, and that would give us 475 watt hours per day. 475 watt hours per day. So this will be the average DC load. Then the average AC load, we have to look at it. How many AC loads do we have? We've got 3 of them. We've got 55, all right, for a day. But then what you will notice is that for the other 2 AC loads, we don't have daily energy consumption. So let's use weekly. So we have 385 watt hours weekly for the second light, the AC light, plus 2,250 for oven energy consumption, and then 1,200 for the steam iron energy consumption. If you add all of those together, that would give us total weekly consumption. So if you add those together, it should give us, that will give us 3,835 watt hours. That would be the average AC load on a weekly basis. Now, if we need to find the average AC load on a daily basis, you just divide that value by 7. So that gives us 547.9 watt hours per day. So you can see now we've been able to find the average DC load per day and then the average AC load per day. Now the next question says we should find the peak find the peak load to be satisfied, the average load and the peak load to be satisfied. So to find the peak power, let's start with the peak AC load. The first AC load is 11 watt, the second AC load is 500 watt, and then the third AC load is 800 watt. To find the peak power, it will be the addition of all of these AC loads or AC power. So that's why we have 11 plus 500 plus 800, and that gives us 1311 watt. That is the peak AC load. Now to find the peak DC load, it will be the DC power, which is 75 watt here, plus the second DC power, which is 50 watt. So since we are looking for peak load, we have to consider the starting current for the water pump. If the power rating for the water pump is 50, is that the maximum power consumed by the water pump throughout the day? No. This may be the average power, this may be the power consumed, but then what is the peak power? We have to find that power at the 6 ampere start current and compare it with this 50 watt. Okay, if the PV is 12 volt and the starting current is 6 amperes for water pump, when we start the water pump, that means the power the water pump will consume at that time will be 6 amperes for current multiplied by voltage to obtain our power. You remember, power is equal to current multiplied by voltage. So the peak DC load for water pump will then be that 6 ampere current multiplied by the voltage, which is 12. That gives us 72 watt. So you can see now we have 2 watt for water pump. The one which is 72 watt, which will be the power drawn or consumed when the water pump is started before it stabilizes to 50 watt. So when we are looking for our peak power, it will be 75 plus 72, not 75 plus 50. 75 plus 50 would be the average power that the average DC power. But when we are looking for the peak power, the water pump will have a peak power when it is started, and when it is started, the current is 6 amperes, and that will draw about 72 watt. So peak power will therefore become 72 plus 75, and that gives us 147 peak DC load, peak DC power for the DC appliances. Okay, so this is very important. Pay attention to that. The maximum power occurs when the pump starts, and that is going to be 6 times 12, which gives us 72. Because 72 is greater than 50 watt, then that's what we're going to use. Because then we are going to use 72 to find our peak DC load. I would encourage you to go over these 2 examples that we have treated over and over, so you can understand what is going on there, and make sure that you get all the necessary details that needs to be obtained. If there are questions, if there are things that you need clarifications about, don't hesitate to send the questions. One way or another, we will find a way to solve those questions. Now, we just completed our discussion on the electrical load consideration when designing the PV system, or when planning to install a PV system. Now we want to consider the absorbed solar radiation. Okay, this is the second consideration we have to pay attention to when designing the PV system. Absorbed solar radiation on the PV surface depends on about 3 major factors. The first one is the incident radiation, the second is the air mass, and then the third is the incident angle. The incident angle is the angle between the sun's rays and the normal on a surface. The normal on the surface is referred to as a perpendicular line. So the perpendicular line on the surface is what we call the normal on the surface. We will not look at the angle between that normal and then the angle that the sun's rays makes with the surface. That angle is what we refer to as the incident angle. Okay, the air mass is the length of the path through the Earth's atmosphere traversed by direct solar radiation. In addition to the absorbed solar radiation and the electrical load, we also have to consider the cell temperature. Generally, when operating solar cells at elevated temperatures, the efficiency is lowered, the efficiency is reduced. We lose efficiency when the temperature is high. The heat must be removed by some mechanical means, which could include forced air circulation or by water using heat exchanger in contact with the back side of the PV module. These are two mechanical ways via which we can remove heat from the module when the temperature increases. And when we are able to do this, the temperature reduces and then the efficiency of the PV system or PV module can be restored. Then we begin to get the best output from our PV plant. This simply means that at every point in time, we have to find a way to ensure that the cell temperature is always not too high. When it is high, when it is elevated, the efficiency of the system decreases. Then let's move on and try to see how we can connect the dots and how we can size a PV system. The sizing of PV systems include the estimation of the required PV panel area and the selection of the other equipment such as the controllers, the inverters, and so on and so forth. For grid connected PV systems, the inverter size is equal to the nominal array power. For standalone systems, the total equivalent DC demand is obtained by summing the total DC demand and total AC demand, both expressed in kilowatt hours per day and converted to DC equivalent. We're going to look at an analysis and example together and then try to use that to explain how you can size a simple PV system. Here is an example that we can evaluate together. A PV system is using 80 watt 12 volt panels and 6 volt 155 ampere hours batteries in a good sunshine area. The battery efficiency is 73% and the depth of discharge is 70%. If in winter time there are 5 hours daylight, estimate the number of PV panels and batteries required of a 24 volt application with a load of 2600 watt hours. What you will notice from this question is that the total load estimation has been done and given to us. So we don't know specifically what appliances we want to power. The question already stated clearly the total load that will be powered, whatever the appliances are. So we only bother about these 2600 watt hours as total load. Okay. Estimate. Let's read the question. Let's read the last part of the question again. If in winter time there are 5 hours of daylight, these 5 hours represent the duration of time that we can actually collect solar radiation that the PV can work and supply energy. So that's the duration of time that the PV will be operating. If in winter time there are 5 hours of daylight, estimate the number of PV panels and batteries required of a 24 volt application with a load of 2600 watt hours. All right. Now the number of panels required is going to be obtained as follows. We know the total load, which is 2600 watt hours, divided by, first of all, a PV system is using 80 watt and 12 volt panel. Now that 80 watt multiplied by total duration will give us the total, it will give us the total energy that the PV can supply. All right. So if the PV system is using 80 watts and it is going to operate for 5 hours in a day, in one day, total energy the PV will be able to supply will give us 5 multiplied by 80. And that's what we have here. 5 hours per day multiplied by 80 watts per panel. That will give us 400 watt hours per day per panel. Okay, so each module or panel can supply 80 times 5. This is very important. That is 400 watt hours. Now from the question here, we have been told what the total energy consumption would be. So to meet this energy consumption of 2600 watt hours, how many panels would we need to connect together to meet up with this particular load demand. It will just simply be the total load demand divided by the load supply by one panel. And that's why we have 2,600 divided by 5 times 80 or divided by 400. If you do that, you would obtain 6.5. And since we cannot have 6.5 panel, we can only have whole numbers to represent the number of panels that we're working with. So we can run this off, we run this up to 7. And so if we have 7 panels and each panel is producing 400 watt hours per day, that simply means 400 times 7 will give us 2,800. The entire PV system will therefore be able to supply 2,800 watt hours, which is enough to meet these 2,600 watt hours demand on the PV. All right. Again, you might want to go over this lecture, this example, this explanation again. And if you have any question at all regarding this, do not hesitate to pop it up and let's look at it together. Okay. Now, because the system voltage is 24 volt according to the question, and each panel produces 12 volt, that simply means we have to connect 2 panels in series so that we can get that 24 volt that the system is required to have. Okay, so 2 panels need to be connected in series to produce the required voltage. So an even number is required to produce the required voltage. This would mean that an even number is required. Therefore, the number of PV panels is increased to 8. Okay, this is very important. Don't forget, we had initially calculated that we need 6.5 panels, and we said we cannot have half panel or a panel that is not a whole panel. It has to be a whole panel. Okay, so we rounded this up to 7. But then now we have realized that the system application, the entire system is about 24 volt. To have that 24 volt system, it simply means that we have to connect 2 modules in series. And what, because one module is 12 volt. So if we do that, 2 panels, you connect 2 panels in series to get the 24 volt. Now, if you do that, it simply means we have to have 2 panels. If we have the first 2 panels, the second 2 panels, the third 2 panel, that will give us 6 panels already. Then there's one more panel, which is the 7th one. It cannot stand alone, because if it stands alone, the voltage rating would be 12. So we need one more panel to be added to the 7th panel so that we can have a 24 volt voltage through on that particular row. So that would give us that would mean that we have to add one more panel to make it 8 panel. An even number of panel will be needed. Okay, so if we add one more panel, it simply means total panel will need for this design to meet this load will be 8 panels. We cannot use 6 panels, because once we use 6 panels, we will not be able to meet up with this load. Our calculation already says 6.5. So if we choose 6 panels, we will not be able to meet up with this load. To meet this load and be on the safer side, we need 8 panels. And your final answer for the number of panels needed will not be 7, it will now be 8. If you are working in an exam or you are analyzing a project that should be submitted and evaluated, if you get 6.5, you get a portion of the mark. If you run it up to 7 panels, you get a portion of the mark. Then if you let us know that we need 8 panels and why we will need 8 panels, then you get your full mark. So pay attention to this and try to understand how it works. Then if for the location with good sunshine, we consider that 3 days of storage would be adequate, then the storage required will be given as follows. Because we were asked to find the number of batteries that will be required too for this PV system. So to get the number of batteries required for this system, first we have to find out the days of autonomy. The days of autonomy would mean the number of days the battery would be strong enough to supply energy in case the PV is not supplying enough energy. And we have chosen our autonomy here as 3 days. Okay, so that's why we said we are considering 3 days of storage for the battery. Okay, so if we are considering 3 days of storage, total load to be supplied is 2,600 watt hours per day, multiplied by the 3 days of autonomy, divided by the battery efficiency would give us total energy that we need from the battery. It will give us total energy we need from the battery. Okay, that will mean that we have to supply this 2,600 for 3 days. We are supplying this 2,600 for 1 day, and since we have 3 days of autonomy, that means we must supply it for 3 days without interruption. So we multiply this 2,600 by 3, divided by 0.73, divided by 0.7. And when you do that, you would have 15,264 watt hours. So the total number of batteries we would need must be able to supply this amount of energy in these 3 days of autonomy. Okay, so number of batteries required will be total energy required by the battery divided by the energy of one battery. That will be equal to voltage times current times time. All right, so and that will give us a total energy, that one battery is producing. Total energy that one battery is producing. So 155 times 6 is what we're going to have here for one battery. If we have 15,264 divided by 155 divided by 6, it will give us total number of batteries we need to meet up with this 15,264 watt hours. So that gives us 16.4 batteries. We do know that we cannot have half battery, so we cannot have a battery that is not a whole. You can't divide a battery into 3 or into 4 or into pieces. Okay, hence we round this up. We cannot round it down because this is already more than 16, and if you will be able to meet up with this energy, it has to be exactly this or a little bit more than this. So we round this up to 17 batteries. Again, as the system voltage is 24 volts from what we do know in the question, and each battery is 6 volt, we need to connect 4 batteries in series to meet up with this 24 volt. So what you notice is that each battery is 6 volt, system voltage is 24. 24 divided by 6 will give us 4. So that means if we connect 4 batteries in series, we'll be able to get these 24 volt that we need. So when you look at the 17 batteries we have, can we connect 4 batteries in series and make up these 17 batteries? 17 divided by 4 will give us 4 point something. Okay, so that simply means we have to choose the nearest figure. We either use 16 or we use 20. Between 16 and 20, we have to choose one. Then the question becomes, which one do we choose? We cannot choose 16 because it will give us less energy than the energy required. If you use 20, you will spend more money, but you will be certain that you are meeting your energy requirement, the energy demand on a daily basis for the period of time that it is needed. So as the system voltage is 24 volt and each battery is 6 volt, we need to connect 4 batteries in series. The number of batteries to use here is either 16, which is very close to 16.4, with the possibility of not having enough power for the 3rd day, or 20, which will give us more safety and security and comfort at the end of the day, or maybe a bit more energy, and that is perfectly fine. So the example is easy. If by any reason you think it is complex, all you need to do is just go over the example again and again. Go over this example again and again, and you would be able to get the best out of it. Feel free to post your question in the comment section. I am going to be available to attend to those questions, and any other person who is also taking part in this lesson can, respond and comment on your questions. What you will find out here, summarily, we've been able to find total number of panels we need to connect together to meet with this load of 2,600 watt hours using the specifications we have in this question. And we have also been able to find total number of batteries that will be required to meet up with this load for 3 days autonomy using the parameters in this question. So 20 batteries would be needed, 8 panels, 8 PV modules or panels would be needed. All right, let's take it a step further. So using the data from example 9.5, which is exactly this example, estimate the expected daily energy requirement. The efficiency of the various components of the system are given as follows. We have the inverter efficiency to be 90%, we have the battery efficiency to be 75%, and then we have the distribution circuit efficiency to be 95%. Find the energy requirement or estimate the expected daily energy requirement using data given to us in this question. And from the data given to us in this question, these are the parameters we're able to find. We're able to find the energy per day, energy per week. We're able to find the average DC load already. We're able to find the average AC load already. We're able to find the peak DC load already and the peak AC load. So with all of these parameters, all those things that we have obtained and found, we'll use them in addition to the new data that we just obtained from this project or question, and then we'll move on. And then we'll be able to solve the problem. Here is it. The average DC load is 475 watt hours from what we calculated, and the average AC load is 547.9 watt hours from our calculations. The average, this gives a total load of 1022.9 watt hours. So total load required will be the addition of the total AC load plus total DC load, and that gives us 1022.9 watt hours. The expected daily loads will be given as follows. The expected daily load from the previous calculations we did are as follows. The day DC, 100 watt hour from the previous system. Night DC will be 375 watt hours. Night AC will be 55 watt hours. Day AC will be 492.9 watt hours. This 492.9 watt hours is from the oven and the iron. So, and those are actually they are used weekly. For oven, we obtain 2,250 per week, and then for the iron, we obtain 1,200 per week. If we add both of them together and divide by 7, we would obtain the daily AC power required during the day, and that gives us 492.9 watt hours. Okay, the various energy requirements are obtained as follows. For the day DC, it simply means the DC energy that is required during the day. What will be the energy requirement for DC during the day? There's another DC we have that is during the night, by the way. So during the day, what is the day DC? This during the day, you will notice that the only DC we are using during the day is the water pump. You will notice that the only DC we are using during the day is the water pump. Okay, and that is 100 watt hours. The other DC is used during the night. Okay, so for the day DC, what will be the energy requirement? The energy requirement will therefore be equal to, since it's a DC, the inverter efficiency is not going to matter here. Okay, and the battery efficiency is also not going to matter. We are obtaining DC directly from the PV, and then we are using it during the day. We are not taking from the battery, and then we are not taking from the inverter. So we're just going to use the distribution circuit efficiency to find the energy requirement. So we have EDDC is equal to EA multiplied by the efficiency of the distribution circuit. The EDDC represents the daily DC energy. EA would mean represent the energy requirement that we are looking for. So this is the formula we're going to use. This is daily DC energy equal to the energy requirement multiplied by the efficiency. Okay, so we are looking for EA, which is our expected energy requirement. If we make this a subject of the formula for this equation, it becomes EA will be equal to EDDC divided by the efficiency. Okay, efficiency is 0.95, that is 95% divided by 100. It will be 0.95. So EA will be equal to 100 divided by 0.95. Don't forget, we had said that the daily DC energy is 100 watt from the previous calculations we did. This is what we have right at the top here. So that gives us 105.3 watt hours will be the energy requirement. Okay, for the night DC, there is only one more DC. DC energy is taken from the battery. So we have the battery DC energy. The DC energy from the battery to meet that load will be equal to the expected energy requirement to meet that load multiplied by the efficiency of the battery and the efficiency of the distribution circuit. Okay, the efficiency of the distribution circuit will be applicable for all the calculations, but for battery it would only be when we are taking DC, and then for others would only be when we are taking AC. Okay, so if we make EA the subject of the expression here, the EA, which is energy requirement, will be equal to the DC energy from the battery divided by the two efficiencies that we have, which is 0.75 multiplied by 0.95. The efficiency of the battery is 75%, so that's where this 0.75 is coming from, multiplied by the efficiency of the distribution circuit, 0.95. So at the end of the day, what you would obtain here is 526.3 watt hours. The ninth DC energy requirement will therefore be equal to 526.3 watt hours. Then when you look at the ninth AC, okay, so to find the ninth AC energy, there's only one appliance that is used in the night and is AC, and that is the light that we use it in the night. Okay, it is 55 watt hours per day. That's what we use for the light that is used in the night. So the ninth AC energy requirement is what we're looking for now. This is what it will look like. Ninth AC energy requirement is obtained by using this expression. Since it is AC, we're going to use the efficiency of the inverter. Since it is used in the night, we're also going to use the efficiency of the battery because it is used in the night when the sun is not shining. And then we're also going to be using the efficiency of the distribution circuit. Because it is an AC, we are going to use the efficiency of the inverter. And then because it is in the night, we are going to use the efficiency of the battery. Because first of all, we are going to get the DC energy from the battery before the inverter converts it to an AC. So we're going to use also the efficiency of the battery for this calculation. And then when all the conversion is done, it goes to the distribution panel. So we're going to use the efficiency of the distribution circuit too. So you will see that we have the 9 AC will also be the DC energy of the battery will be equal to the energy requirement multiplied by the three efficiencies: efficiency of the battery, efficiency of the inverter, and efficiency of the distribution circuit. If you make EA the subject of the equation, EA representing the expected energy, expected energy requirement, it will be equal to 55, which is the DC energy, divided by 0.75, 0.9, and 0.95. And that gives us 85.8 watt hours. Then we do the same thing for the day AC. For the day AC, there are only two appliances, there's the oven and the iron. And we have calculated the day energy requirement. If it is the day AC, that means we're only focusing on the inverter and the distribution circuit. It is during the day, so we are getting our energy from the sun, not from the battery. Okay, so what we find out is that we have the same equation. It will now be AC energy, the daily AC energy will be equal to the energy requirement of the AC appliances multiplied by the efficiency of the inverter and efficiency of the distribution circuit. If you make EA the subject of the expression, it gives us 492.9 divided by 0.9 divided by 0.95, and that gives us 576.5 watt hours. So what you will find out is that we have seen for each of the appliances, we've been able to calculate all the daily energy requirement. So the expected energy requirement for all the appliances, since we already know for each of the appliances, for all the appliances and for the PV that we have installed, will therefore be equal to addition of all the individual energy requirements that we calculated for each load. That gives us 105.3 watt hour plus 526.3 watt hours plus 85.8 watt hours plus 576.5 watt hours, and that would give us 1293.9 watt hours. 1293.9 watt hours. Therefore, the energy requirement is increased by 27% compared to 1022.9 watt hour estimated before. Now, what this means is that at the beginning, you will notice that we estimated a total of 1022.9 watt hours at the beginning, okay? And then when we now decided to consider the use of the inverter and then the use of the battery and the distribution circuit and the efficiencies, so we became more specific about the requirement for each load, and we were able to obtain it to be 1293.9. This is higher by 27% compared to the first calculation. So when you're looking for the daily requirement, this is what to do. It is advisable and better we go through this method, or we use this method rather than this method to find the expected energy requirement. It is important that we quickly look at some of the future thoughts about solar PV. Solar PV in the future will have better performance characteristics. One of the reasons we said this is that it will be integrated into building materials. For example, the roof shingles, the windows, the walls, and this will give us a technology called the Building Integrated Photovoltaic Systems, BIPV. All right, and that has already been in existence now, and that is currently, as we speak, that is in existence already, and quite a number of buildings are integrating PVs, especially in countries where the policies support such. There will be flexible panels which will be useful for backpacks, for awnings, for clothes, so that simply means you can have your bags as one of the applications where you can add a PV. You can actually install the PV on your bag, and then when that happens, that means you can charge your phone with your bag, with the PV installed on your bag, okay, and then the PV would have a battery, and it would work probably just like the battery bank works, and so on and so forth. Then we have thinner layers, and then carbon-based PVs would also be available. We already have the thin film layers, by the way, thin film PVs. So all of these are important features of what we expect to see in the future, and the future is already now. As we speak now, most of these technologies are already available. Most of the PVs we have studied, most of the PVs we have, and the PVs we have studied are silicon-based. In the future, there's a possibility to have carbon-based PVs. With this, we have come to the end of this session, and I want to encourage you to go over this session, this teaching again and again and again. If you are here and you enjoyed this video so far, please give it a thumbs up. If you have not subscribed, I encourage you to subscribe to this channel. Let me know what you think about photovoltaic solar technology. Do you think the investment in PV is worth it? Do you think it is possible to do away with other conventional technologies and just focus on the use of PV? Can PV actually solve the problem of electrical energy globally, especially in the rural areas and in the modernized areas where energy consumption is increasing on an alarming rate? Let me know what you think, and I hope to read from you in the comment section. See you in the next lesson.